Have you ever wondered how an app on your phone goes from just a few people using it to millions, all without completely falling apart? Well, today we're going to pull back the curtain on the secrets behind those massive systems that run our digital world, everything from social media to your favorite online store. So let's say you've built a fantastic app. It's taking off, people love it, users are pouring in. What's the single biggest danger you're facing right now? You might think it's a competitor or a nasty bug, or maybe even a security threat. But it's none of those. It's something way more fundamental. Believe it or not, the biggest threat is your own success. You see, the design that worked perfectly for 1,000 users is going to buckle and collapse under the weight of 1,000,000. That one server that was your trusty workhorse, it's about to become your single biggest bottleneck, leading to slowdowns, crashes, and a whole lot of unhappy users. And look, this isn't just some theory. Amazon famously found that for every 100 milliseconds of delay, that's literally faster than the blink of an eye, their sales dropped by 1%. Performance isn't just a nice-to-have feature. It's the absolute foundation of the business. So the real question is, how do you build a foundation that won't crack under all that pressure? Okay, so we know performance is everything, and we know that a single server just isn't going to cut it forever. This brings us to our first huge challenge. How do we actually handle all that growth? The answer is a concept called scaling. But, and this is a big but, it's not as simple as just buying a bigger computer. The way you choose to scale is one of the most important decisions you'll ever make. You've really got two main paths you can take. The first is vertical scaling, or scaling up. Think of it like swapping out your car's engine for a monster V8. You take your one server and just make it more and more powerful, more CPU, more memory. It's simple, sure, but you eventually hit a wall. And worse, you've created a single point of failure. If that one super server goes down, your entire app is dead in the water. That's a massive risk. Which brings us to the other way, horizontal scaling. So instead of building one giant server, you use a whole fleet of smaller, identical ones, and you just spread the work out among them. This is hands down the way to go for any system that's expecting growth. Why? Well, for one, you can add new servers without any downtime. And if one of them fails, no big deal. The others just pick up the slack. But of course, every solution creates a new problem. Now, all of these different servers need to talk to each other. And that question right there, that question leads us to one of the most fundamental laws of building large-scale systems. Because the moment you solve the server problem, you're immediately faced with a new, unavoidable truth. The network itself is unreliable. Right, because once your data is spread out across a bunch of different machines that are all talking over a network that can fail at any moment, you run smack into some hard theoretical limits. It turns out you just can't have it all, and this impossible choice is perfectly captured by something called the CAP theorem. So, the CAP theorem basically says you have three things you want. Consistency, meaning everyone sees the same up-to-date data. Availability, meaning the system always responds, and partition tolerance, meaning it still works even if the network between servers gets disrupted. Now, the punchline of the whole thing is, you can only pick two. But here's the real catch. In our world, networks fail. It's a fact of life. So partition tolerance isn't really a choice. You have to have it, which forces you into a really tough decision. The real trade-off is always between consistency and availability. A CP system, like your bank's app, will always choose consistency. If there's a network problem, it would rather show you an error message than risk showing you the wrong account balance. That would be a disaster. On the other hand, an AP system, like a social media feed, chooses availability. It will always show you something, even if that post is a few seconds out of date. Because let's be honest, seeing a slightly old post is way better than seeing nothing at all. Okay, so we've established a pretty important fact. Failure is not an if, it's a when. A server will crash, a network will drop packets. And accepting that requires a totally different mindset. Great architects don't just hope for the best, they actively plan for the worst. They build systems that can handle failure using what are called resilience patterns. The bulkhead pattern is a brilliant example. The idea is literally stolen from ship design. You know how large ships have watertight compartments? If one part of the hull gets a hole, it floods that one section, but the whole ship doesn't sink. We do the exact same thing in software. We isolate parts of our system, so if one non-critical feature starts failing and hogging resources, it doesn't take down the whole app. The really important stuff, like logging in, stays afloat. Next up, we have the retry pattern. And it is beautifully simple. If a request fails because of some temporary glitch, like a quick network blip,
the system just waits a second and tries again. It's kind of the software equivalent of, have you tried turning it on and on again? And you would be shocked at how many problems this simple little trick solves.
But what if retrying doesn't work? What if a service is just completely broken? Well, constantly retrying is just going to make things worse. You're just hammering a system that's already down. That's where the circuit breaker comes in. Just like the one in your house, if it detects too many failures in a row, it trips the breaker. It just stops sending requests to the broken service altogether, which protects the rest of the system and gives that failing part a chance to recover. So at this point, our system is scaled out, it's resilient, but it's also incredibly complex. It's not one program anymore. It's a giant spider web of tiny little services all talking to each other. So when something inevitably goes wrong in this mess, how in the world do you figure out what happened? You can't fix what you can't see. You're flying blind.
This is where we need what's called observability, and it comes down to 3 main pillars. Think of yourself as a detective. First, an alarm goes off. Your metrics tell you what is wrong. Hey, CPU usage is at 95%. To figure out why, you look at your logs. They give you the detailed story. I see a flood of database connection failed errors. But in this huge web of services, which one is the culprit? That's where traces save the day. They show you where the problem is by following a single request as it jumps from service to service, pinpointing the exact spot that's causing the bottleneck.
And this highlights a really critical difference. You see, traditional monitoring is all about checking for problems you already know about. You set an alarm in case something happens. But observability, that's for the what on earth is going on moments. It's about having the power to explore and ask brand new questions about your system when it's failing in a way you have never, ever seen before. So as we start to bring this all together, what's the one big idea you should walk away with? It's this. System design is not about finding one single perfect, magical answer. It is a constant balancing act. It's all about making informed trade-offs. The best architects don't just wing it. They follow a clear process. They start by asking the most basic questions. What are we actually building? How big is this thing going to get? Then they sketch out the big picture, they zoom in on the tricky parts, and most importantly, they are constantly on the lookout for bottlenecks and asking themselves, what trade-off am I making right here? It's a disciplined process that turns these big ideas into a solid plan. And that leaves us with the final and most important question. There is no such thing as a perfect system. It's a myth. You simply cannot have maximum consistency and maximum availability and infinite scalability and low cost all at the same time. So the mark of a great architect isn't knowing the right answer. It's knowing which questions to ask to make the right trade-offs for the specific problem you're trying to solve. So, what will you choose to prioritize?